in order to process. So I think most of you guys already learned something about thermodynamics before, right? During the undergraduate program, bachelor degree, have you learned something about thermodynamics before? I think most of you learned something about thermodynamics already, right? It's fine. I can talk. You probably can come to my office. So I will try to talk something different, but honestly speaking, I don't know what's your background. And I don't bother to give you a quiz and test your background. But anyways, I will try to have a mixture. So basically, for the thermodynamics, we are talking about. I always have a difficult to distinguish orally with these two words. So how do you pronounce that? How do you pronounce that one? Microscopic, right? What about this one? Do you think that the people hearing can distinguish very clearly from from the sound, macro and micro? Do you think it's very clear difference? May or may not. But you know the difference between them, right? So this means something we can see from the eye is more like the macro. That means large objects. But the microscope, that means very tiny, we cannot see, right? So basically, when we talk about the thermodynamics, for most of the job we're dealing with the microscope. Gravity is doing the job. We're talking about this part, okay? But if we only talk about that one, probably you will get really confused. Especially when we talk about the entropy. We don't know what's the definition of that. We only know that the entropy is what? What's the definition of entropy? Huh? Yeah, I know, the mathematical.
KB log of
Then you go to the microscope. I'm talking about from the macroscopic point of view. What's the definition of it? It's something like that, right? dq something, if that is a resolvable process, it's a TDS, right? That's the way we define the entropy, right? That's the only thing we know, right? But that's only the thermodynamics tells us, correct? But if we want to know what's the definition of the S, we need to understand the microscopic property of the system, okay? And for this part, we call it the thermodynamics, okay? And for this part, we call it statistic. Statistics, okay? We call it statistical physics. I'm trying to touch a little bit on this area, but not too deep, okay? We're going to talk about distribution. We're going to talk about how we define the entropy. Actually, the most important thing from my personal experience, the most difficult part is definition and understanding of entropy. You know what I'm saying? For the energy and the work, the VDT, the VDP, whatever, PDV, or whatever, that kind of stuff, that's easy to be understood, right? We do some work to the system, or the system do some work to the external. That's really hard, easy to understand. The only most difficult part is this part, and most of the challenges and tricks of thermodynamics come from this part as well. And from the entropy, we can also define what free energy, right? We have the Gibbs free energy. We have the Helmholtz free energy. We have two types of free energy, correct? And why we have defined the free energy? Why the energy itself doesn't work? We need to define free energy. All come from this term, right? So I think the majority of the part we're going to explain this term from different kind of angles and apply this concept to different systems, like ideal gas, like solution, even semiconductors. Okay, you will find actually they all work the same way from the thermodynamic point of view. Although different systems have their own characteristics. But if you go to thermodynamics, you'll find the same thing. You know that have you heard about this kind of terminology? Okay. So if we have a partially, so we have the film here, okay, a partially permeable film, okay. Probably the sodium ions can pass through this film freely, okay. We have water, fresh water on this one. We have salt water on this end. What will happen? The water will go to this end, right? And then what? The liquid level will build up, and this one going down, right? And we build up what? Build up pressure, correct? Because the liquid level became from each side, correct? So what's the name of the pressure? Huh? Yeah, that's right. So what's yeah, osmotic, right? Pressure. Okay. See that one? Because the density of the sodium ions from this end and this end different, correct? This is from liquid. Let me tell you another thing. Who do not know what is a diode? In the computer, you have P junctions, we have diode. Do you know what's the principle of the diode? What's the function of the diode? Electrical diode.
To allow the flow of electrons, to control the flow of electrons.
To control the flow, to more specifically? The function of the call is rectification, right? Is only allow the current to go through one direction and the other.
Yeah.
If you measure the IV curve, this is V, this is I, you give the voltage on the diode, the IV curve looks like this, right? Exactly like this. And it looks, the diode looks like, okay, you have two pieces of the semiconductors, it's made of silicon, okay? One is a P-type, the other is N-type. You don't know too much about what the N-type is, what is N-type. But I tell you, in the N-type, you have more electrons than the P-type, okay? And if you put them together, what will happen? If you put them together, what will happen? The electrons will go to this way, correct? And you have more electrons this side, right? And previously you have more electrons, but electrons start to flow to this direction. And then you also build up the pressure. But it's not the mechanical pressure anymore. It's the voltage, okay? It's the electric voltage. Exactly the same picture, okay? You can see the total different thing. This is electrical components. This is just a tank of water, but they follow exactly the same thermodynamic law, okay? The same thing, if you, I know quite a lot of people have a background in the mechanical engineering. So we have another class next semester. I'm going to teach that one as well, although I really don't like that class because I'm not the very professional now, honestly speaking. I do not do the relative research. I'm teaching the phase transformation. Okay, so basically we use that one as well. We use this kind of entropy, free energy argument all the time. Okay, you can see that we use the thermodynamics to explain quite a lot of the phenomena there as well. Okay, but again, back to the topic. So all this one is the microscopic description of the different kind of thermodynamic systems. And then, but if you understand what's the reason for that one, we need to talk something about that. Okay? But again, so this is not our main topic. I just borrow some concept from the statistics to explain why we define this kind of really weird parameter in thermodynamics to give you a better picture. But somebody already told us the definition of entropy. Who told us? You told me? Yeah, or you told me. Who told me? Who told me the definition of the entropy? I think there's one person just told me it's the log in K log in whatever. Okay. So basically, I repeat again. What's that?
KB ln of
K what?
a K ln of multiplicity.
N?
Omega.
Omega N? That's it. Okay. K is what?
Boltzmann.
How many of you already know this equation? Can you raise your hand? How many of you already know this equation? Some of you? Okay. So K is the Boltzmann constant. So you know this one, right? R is the ideal gas, constant. So this one is equals to what? Na times K, right? Na is what? Is the Avogadro constant, okay? K is the Boltzmann constant, okay? And omega, this is something different. Omega, that means under a given microscopic state, how many microscopic configuration you have. Okay? So this is the definition of the entropy. Okay? I'm going to derive this this equation for you guys, but you don't need to memorize it. Okay? I cannot memorize it either. It's so complicated. But anyway, so for this class, I just give you a global view of what we're going to talk about for this semester. And what's the make the definition of the key concept first, okay? So once again, I will try my best to avoid the use of the slides. The reason is the slides can change. I can change the slide very fast, and I need to go back and forth, and nobody like it. I don't like it either. I don't like it. I mean, when I was in college, if the professor used the slides, I really hate it. I mean, because I cannot follow. You know what I'm saying? So I probably the best, especially for this fundamental class, I think the best way for us, the best practice is I still write everything on the whiteboard. Hopefully my handwriting is still acceptable, you can recognize them. And I have a lot of spelling mistakes. Unfortunately, I'm not native speaker, as you can help. I mean, but if you identify any kind of the mistake, feel free to tell me. Okay, you can tell me in front of everybody, just to put shame on me, no problem. I don't worry about it. Okay, I'm a shameless person. Don't worry. If you feel shameful, you are not qualified for the teaching job. Okay, you should feel shameless. Doesn't matter. Okay, and you should be brave enough to accept your mistake. The other thing is my pronunciation also have a lot of issues. Okay, I mean, back to the Georgia, the student that we have, hey, the pronunciation is wrong. Thank you for telling me. That's good. Okay, I have quite a lot of difficulties. So, for example, I have a long time I don't realize I did not pronounce this word correctly. How to pronounce this one? Unique, right? And I was always thinking unique, and people were talking about. I mean, and only one student has okay. The right pronunciation is unique. Oh, I see. Thank you. And then everybody correct me. I mean, even when I go to the dining hall, what do they want? I want the cucumber. That's cucumber. Okay, thank you. And then people call me, I mean, the bus driver, and I said, hey, where you come from? Originally I'm from he told me, oh, okay, from Colorado. Oh, as you come from Colorado. And then, no, Colorado is not Colorado. Okay, good to know. Anyway, so the first thing we want to answer is, so how many of you already learned some of the fundamental physics before? College physics. You know mechanics, right? You know, everybody should know Newton's law. Am I right? You know how many Newton's law? 3, right? What is first law? Inertia. Second law? After you have MA. The third one? Yeah, action equals to reaction, but in the opposite direction. Correct? That's Newton. So we have mechanics. How many of you learned electrodynamics or electromagnetics? The computer science or electrical engineering should learn that already, right? But let's talk about Newton's law, okay? So if I only have one object, think about the entire universe, only have one object. There's nothing to describe, right? It's only one object, it's very lonely, there's no interaction at all, right? If you have interaction reaction, you at least have two body, right? If you start to have two body, you start to have the interactions, correct? That's a two-body problem, right? I mean, keep in mind. I mean, just try your best to memorize. When you're dealing with the fundamental physics or fundamental mechanics, how many body, at the most, you have ever been dealing with? Two body. No more than that, correct? We are talking about gravity. Okay, they have object is falling down, right? It's a two-body problem, right? One body is here. What about the other body? It's the Earth, right? You're talking about the Earth orbiting about the Sun, correct? We have two bodies, right? The moon orbiting upon the Earth. We have two bodies, right? Correct? And we will talk about you push a box. You have the inertial. You have the momentum. You have whatever. It's always two-body problems. Although two-body problems are already very complicated, right? We have momentum. How many of you do not know what is momentum? Do you know momentum? Energy, right? We talk about the energy, we talk about force, correct? It's always a two-body problem. What about three-body? It's really complicated, right? You cannot solve it. It's not solvable. At least right now with our hand, right? Full body. No way. 3, 4, 5, 6. Okay? All this kind of problems belong beyond two-body problems. We call them few-body problems. Okay? Few-body problems. As long as the number of bodies is countable, we cannot solve them. Okay? We cannot solve them. The system is so complicated, right? The interaction is so complicated. But I have to tell you one thing. If disorder or like this kind of become very chaotic, okay, system become very chaotic, then the orders start to build up on this kind of very gigantic disorder system. Okay? We cannot solve 3-body, we cannot solve 4-body. But if what about we have 10 to the order of the 23 orders of magnitude? Okay? What will happen? Then we can just change another way to describe the system. Correct? Instead, we do not know the trajectory of each body anymore. But we can see from the macro point of view to see that as a whole piece, correct? As a continuous distributed piece, right? So this is just like what, I mean, this is not the only apply to the object we study, okay? Like not only apply to materials, not only apply to gas, semiconductors, liquid, it's also applied to society as well. How do you think this insurance company operate? Right? Do you think that if we only have 10 probably people there, do you think we establish an insurance company for only 10 people? No way, right? The risk is not predictable, right? However, if you have millions of people surrounding you, you can open an insurance company. That's reason. Oh, by the way, so what's your insurance company? Most of you are graduate students, right? Do you have insurance covered by the university? State Farm? All of you? State Farm? That's required by UCF or something.
Which kind of insurance?
Medical?
I'm talking about medical insurance.
medical.
70s. Yeah.
Oh, it's different from what we have. So for the faculty, I don't know, I thought that everybody have the same insurance cover for the UCF. But for faculty, we have another company. It's not a company anymore. It's provided by the government, I think. It's called People First. Have you ever heard about it? And it's something really weird. I mean, I don't. So but anyway, so as long as you have a lot of people working together, we do not care whether a single individual have accident, have the medical issues anymore. We just care about the statistic distribution. Okay, in this age, what's the highest risk? What's the disease they have? And how much we need to pay in average every year, right? They do the calculation and then charge you, right? Although probably you do not spend you do not go to with the doctor quite often, but you still need to pay, correct? You got all this money determined by the calculation. For you and me, I don't go to the doctor very often, but probably when you get age, beyond 50 years old, we need to visit the doctor quite often, right? You know what I'm saying? But this is all with the statistic behavior. I mean, theoretically, yes, okay. For insurance companies, theoretically, yes, they should do the statistic, but they need to make profit. I mean, they need to make money. So that's the reason they overcharge us, okay? Forget about insurance company. So I have quite a lot of complaint with it. So if I have enough time, I'm going to complain that, insurance company with you guys, okay? But anyway, so the key point is, when the number of the object is large enough, we can change the view to analyze the statistic behavior now. Okay? All right, so next topic, I suggest that you make a note, because I will not post this one online. But if you cannot catch, you can come to an office, or you can just ask other people's notes. Okay? Okay, so we talk about the macroscopic behavior, okay? But how can we describe the macroscopic behavior of the statistic systems? We need to bring some parameters, correct? We need to bring some, we call it the thermodynamic parameters. Okay? I'll give you some example. Or can you give me some examples with the thermodynamic parameters you have ever seen?
Partial pressure, volume.
Yeah. Pressure,
Volume.
volume, something else?
temperature,
Huh? Temperature, something else?
internal energy.
Huh?
Internal energy.
Internal energy. Something else?
Entropy.
Entropy?
Entropy.
Entropy.
Both. Yeah.
Yeah.
Rho or like density.
Density? Yeah, free energy. Density. What kind of stuff?
Rho.
Density parameter. Okay? So this is all thermal parameters. They have a common all of them, all of different they label different kind of properties, different behaviors, right? But there's one common thing. They are defined, I mean, they are independent of the history of the thermal process. You know what I'm saying? So, for example, temperature. I can warm it up, right? I can warm up the your water. So how many ways we can warm up the water? We can just boil it, right? Put on the oven. We can shake it. Okay, as long as your muscle is endurable enough, you can always shake it. We can put it under the sun, right? But in any kind of sense, I mean, in any kind of way, as long as the water goes to the same final state, you always reach the same temperature. It's independent of the process, correct? And this applies to all the parameters here as well. You know what I'm saying? For example, if you give the same temperature for the gas, okay, I'm talking about gas. If you have the same same temperature and same pressure, you always end up with the same volume, right? It's independent about how you warm it up, how you give the pressure, right? It always end up with the same parameter, okay? And this kind of parameter, independent of the history of the system have experienced, we call them the thermodynamic parameter. That means all these parameters are only defined by the final state, independent of what happened to the previous. Understand what I'm saying? Okay. But some parameters, although we use them in the thermodynamics, but we do not call them thermodynamic parameters. Okay. Anybody can give me an example?
Maybe mass.
Huh?
Mass maybe.
Why do you think?
Do it have like some losses with
Yeah.
temperature, but that's like it's kind of tough to explain.
Okay, let me give you an example. Huh? The question is that all these parameters are defined by the final state of the system. If the final state is given, all these parameters are fixed. Right? It's independent of what the system experienced before the final state. Correct? For example, I mentioned you have a temperature. If you want to reach a certain temperature, you can warm it up, you can shake it, you can do whatever you want. Right? But as long as it's reached the same state, the temperature always the same. Correct? Let me give you an example. This parameter, okay? The heat. The heat is a non-thermodynamic parameter for the system, okay? It's still a parameter, but it depends on the process. Okay? One example, let me make this more clear, okay? So for example, I have the eraser here, right? I can move the eraser from this one to this place, right? You know I'm doing some work, right? I push it, I have force, and they have the displacement, correct? I have some force, correct? I did some work. Where's the work go? It becomes what? I did some work. It becomes heat, right? I heat it up. Believe it or not. If you don't believe it, you can try. Okay, everybody can put your finger and very quickly go through your clothes to see whether it got burned. Okay? I don't take any other responsibility for that kind of experiment. Okay? If you have burned your fingers, it's not my deal. It's not my case. Okay? I don't have a liability to case, but if you want, you can try. Okay? I can go from this one to this one. The other, if you want to see the thermal effect, do you have the that kind of receipt from the like the chicken fillet or whatever? They print out the receipt, right? Use your fingertip, the fingernail goes through very quickly. It becomes dark. You have to generate heat, right? That is heat sensitive paint on it. But anyway, so we have here the starting point is here, the ending point is here, correct? We generate heat from here to here, right? So This is the starting state. This is the final state, right? I go from here to here, right? I can also move in that way and to end up here. Do you think we generate the same heat? No. Correct? Because definitely you have more loop. You have longer loop than the straight line, correct? And that's the reason the Q is always depend on the thermodynamic process. It depends on the history of this object has experienced, right? So we cannot use Q to describe the state of the system. Understand something? Yeah, clear to everybody? So if we talk about thermal parameters of a system, Q is not. That's really, I mean, as I mentioned, most of the time we're dealing with a Q. This is the most mysterious number or parameter in the thermodynamics. Q is also related to what? To S, right? From definition of S, the Q related to S, the Q related to the entropy, right? So it's most mysterious. But for other part, it's pretty straightforward. And only this Q and S, they're really complicated. But anyway, so right now you know what is the thermodynamic parameters, correct? Everybody keep in mind. Okay. This will appear in your final examination. Pick up which is the thermodynamic parameters. I mean which one is not. Okay. Okay. So the other thing is, from all the writing, you can see that I on purpose put this parameter in two lines. What's the difference? One is extensive, the other is what?
Intensive analysis.
Why do you still come to this class? Really weird. I mean, I'm finding that I'm just repeating what we already taught. Okay, this is an extensive. Okay? This one is an intensive. Can you tell the difference between these two definitions? What is extensive? What is intensive?
Is one extensive, depends on mass.
Uh-huh.
And intensive.
The other one doesn't. Right? Okay. So I have a cup of water. Okay, cup of water. Oh, you have water. Well, the ice is the ice here. Okay, it's ice. So the temperature is fixed, correct? The temperature is uniform. The signal reaches the equilibrium. And the pressure, what's the pressure of the liquid right now? It's atmospheric pressure, right? Okay, you can see that if I just put half of my cup to his cup, do you think the temperature change? The pressure change? Nothing change, right? I mean, this kind of properties or parameters independent of the mass, as who said that? Does not depend. Or more precisely, it does not depend on the amount of the matter inside the cup. Correct? This is intense, how intense it is, okay? Extensive, that means if the amount of matter increases, that parameter also increases. For example, like volume change, right? The matter of the quality of the quantity of matter increases, the volume changes, right? The total internal energy changes, entropy changes, free energy, enthalpy, whatever, they always increase proportional to the number or the amount of liquid in the cup, right? But temperature, pressure doesn't change, correct? Why this is important? For example, if I bring his cup, put his cup beside my cup, eventually these two systems will reach thermal equilibrium, right? And what does thermal equilibrium mean? They're not necessary to have the same mass, same volume, same entropy, same total free energy, but the intensive parameters always reach the same, right? Pressure should be the same, correct? Temperature should be the same. But sometimes, I'm talking about this open system, but if you close the system, the pressure not necessarily to be the same as well, okay? But temperature always be the same, correct? But it depends on how it isolated two systems. But if I just put his cup and my cup side by side together, then the temperature will become the same. Pressure will become the same. But volume, and energy, entropy, free energy, or enthalpy, they can be different, correct? Any questions? Very simple concepts, right? Any questions?
Do we look at like specific volume and specific entropy and all that stuff?
Yeah, you can. No.
But then that becomes
Think about it. we have the specific thermal capacity, right? That means the capacity, heat capacity per volume, right? So we do not define the specific volume anymore. That is volume divided by volume. Okay, that is one. Okay, but yes, you can define specific internal energy, specific entropy, whatever. Okay, then it's become the intensive. Okay, it's become intensive. Okay, but you will find if, for example, like energy, if you define it by volume, this one will be correlated to the temperature. You always change back to the intensity. Okay. Well, I will explain to you what is the meaning of temperature. Okay. We use temperature every time, every day, but what's the physical meaning of temperature is still not very clear. Okay, I hope that through the class we can also explain what the temperature means. Okay. Basically, temperature measures the mean, the average internal energy of the system per, the average specific internal energy of the system. That's the temperature. But I will give you a more precise definition of it. Okay, so we explain the intrinsic, extensive, okay, that's fine. Okay, so the other thing. Oh, we also talked about what is the thermodynamic parameters, okay? Intrinsic. There's another property of the intrinsic. Not intrinsic. The thermal parameters, okay? The thermal parameters is also, you can see that this is given by the final state of the system, right? In other words, they are intrinsic property of the system. Correct? And that is belong to, you know what is intrinsic mean, right? That's the intrinsic property of the system. Some part is not intrinsic property of the system. For example, like Q is not intrinsic, okay? Defined by the external loops. Okay? And there's another, mathematically speaking, we're talking about thermodynamic parameters. We're talking about something not the thermodynamic properties. I just explained you what's the difference. Okay, this is defined by the final states of the system. This cannot be defined by the final state of the system. Instead, it depends on the detailed process the system experiences. Correct? Right? This is just what I just said. Right? But this is definition. How can we express this kind of idea more precisely in a mathematical point of view? We're talking about some theory. We need to use math, right? What's the difference? What's the difference between mathematical point of view? What's the difference between thermodynamic parameters and the non-thermodynamic parameters? Mathematically speaking, if you can do the full derivative of this parameter, for example, dp, you can define, for example, for a system, okay? The V is what? Is a parameter of P and T, okay? For the ideal gas, for the gas, okay? We know that pressure, if you compress it, the volume will change. If you increase temperature, the volume can also change. This is how your engine works, right? And we know that if we want to calculate the dV, the small deviation or small differential, differential of the V, what's it equals to? This one equals to partial V, partial P, and with a constant T, dP, plus partial V, partial T, as a constant P and dt. Right? Everybody knows the differentiation, right? Okay. Is that correct? And this expression we call, this kind of the formula of expression, we call it exact differential. Okay? As long as the parameter can be written in that form, yes, it is exact differential. In other words, it's a thermodynamic it's a thermodynamic parameter. Okay? But for Q, we can define dq. Okay, dq is to what? dq equals to, for example, like still talk about the force. Okay, we have the friction we have the displacement, correct? Is that right? But this one is not exact differentiation. What's the reason? Because if you do the integration, delta Q equals to F and L. This integration depends on the detailed loop, correct? But for that one, if you do the integration, for this one, if you do the integration, this one simply equals to V final minus V initial, right? Independent of the loop, correct? We don't care about how the system evolved. Got my point? And in other words, this is a very specific definition of Q. We have different Q, okay? We even do not have a proper expression or definition of Q, okay? This is just for the full friction and displacement. And for some cases, we even cannot give the expression of Q. For example, you just put two cups together. You put his cup and my cup together. How do you define the dq? There's no way to write it out, right? There's no way for you to do the expression here, at least right now, right? But eventually we know that for the ideal case, for the reversible process, the dq equals to TdS, okay? But you will know that TdS is kind of the, ds is one exact differential parameter, exactly differential. That means this is thermodynamic parameter, but dq is not, okay? dq is not. In other words, dq is not exact differential, okay? But dq divided by t is, okay? So then this becomes a thermodynamic parameter. We name it entropy. I know that you still got to do it. But anyway, so I will try my best to explain, to give you more examples through the semester, right? But as I mentioned, this class is just like the introduction, okay? It just give you a global view about what we'll talk about this semester, okay? All right, so any questions? I think we have a lot of question mark here, but hopefully not. Huh?
I don't have a question, I just couldn't see.
Oh. Oh, by the way, what am I talking to you can find on the textbook, the first chapter introduction. Okay? I'm just talking about what's inside the book. I'm trying my best to follow the book. Otherwise, you may have a complaint. I don't follow the textbook.
Over there you said dq is not a thermodynamic property, but dq divided by t.
If the parameter can be expressed as exact differential, it can be considered as a thermodynamic parameter. Okay, but if not, no. Okay, that means they are equivalent. Okay, a parameter can have the form of exact differential. Then it's a thermodynamic parameter. Then it's the intrinsic property of the system independent of the history. Okay? If a parameter cannot be written in a way of exact differential, it's not a thermodynamic parameter, and it depends on the detailed history. Okay? The most important example we to memorize is the Q, the heat. Okay? It's not a thermodynamic property. It cannot be expressed as exact differential, and it depends on the detailed process, okay? And temperature, volume, pressure, entropy, enthalpy, internal energy, free energy, all these parameters, they are intrinsic properties of the thermodynamic system. And then all these parameters are thermodynamic parameters. And all these parameters can be written in the term of the exact differential, okay? All right, so basically we define some terminologies. We want to everybody have the same common language so we can start our discussion, okay? Common language is very important because if you speak different languages, we cannot build up the system, okay? For example, I will give the class in Chinese. Can anybody understand? Right, so I have to learn English and in order to express my idea to you guys, okay? But anyway, so I'm just feel curious. How many different languages is that in this room? What's the language you speak? Your mother tongue. How many of you speak Chinese? We have two. What about English? French? German? Okay, kind of. And the Hispanic? Espanol? Okay. Something else? Some language else?
Bengali.
Okay. Hindi? Okay. It's got Hindi or Hindu? Hindi, okay. How many languages in India? There are thousands of languages.
1600 approximately. So.
Oh, okay. That's number is not as large as number of gods, right? But I know that in India you have three major gods, right? The creation, the maintain, and the destroyer, right? Yeah, I know quite a lot of the Indian stories because my PhD supervisor, Indian guy. Anyway, so okay, so but we have these parameters. This is only definition. It's so abstract. Okay, we need to give. When we study the object, we need to have some. When we study the class, we want to build up the system. We need to have some examples, right? We need to have some examples to study with, right? So the most important, most simple example when we start talking about thermodynamics is the ideal gas. Okay, it's the ideal gas, right? What's the ideal gas? So model is just like we have a gas. They have no interactions. It's just like the exactly the same particles freely flow inside the room, freely flow in the box. Okay, these small particles, they have no internal interactions. Okay, it's just freely flow in this kind of container. So that's the ideal gas. Okay, and we find that for the ideal gas, how many parameters we need to describe the system. Okay, as I mentioned, so for thermodynamics, we know that from our experience, how many different parameters can this can be used to describe this tank of the ideal gas?
Is it usually two and then you can find everything else?
Yeah. Two. What's the two?
Pressure, volume.
Pressure and volume. Okay. So what's the relationship between? I mean, the other one. What's the other one? Temperature, right? Something else? Nothing else, right? That's good enough. Okay. As mentioned, this ideal gas. There's no other degree of freedoms. Okay. They just move. They only have the translational movement. Do you know what is translational motion? Translational motion means I move from here to here in the x, y, z space. Okay. Of course, you have other degree of freedom. You have the rotation. Okay. But since they are the small particles, they do not rotate. Okay. So then we only have this kind of degree of freedom. We only have 3 degrees of freedom x, y, and z. Okay. So 3 parameters is good enough. Okay. So if we keep a constant t, what's the relationship between p and v?
Inverse.
Any ideas? What's the relationship between p and v if the temperature is fixed? From your experience, okay? So you have this kind of tank. The temperature is same. If I compress it, what will happen? The pressure builds up.
Yeah.
Right? This is your cylinder, right? The car cylinder. Right? And what's the relationship? And you know that the P going down and the V goes up. So what's the volume? What's the relationship? I mean, what's the relationship between these two?
Boyle's law.
Huh?
Boyle's law.
Yeah, Boyle's law. But what's the Boyle's law tells us?
It's inversely proportional.
Yeah, this one called Boyle's law, right? Is the P times V is a constant, right? The more you compress it, the larger the volume, right? Okay, right now, okay, remember this T is what? This T is an intensive parameter, right? P is the only extensive parameter here, right? What about P? If I keep a constant P, what's the relationship between T and the V? If I keep a constant pressure, what's the relationship between volume and temperature?
Proportional?
Proportional?
Inversely proportional.
Inversely proportional?
Proportional, yes.
Okay. Proportional? What's the name of that law? Charles' law? I know the name on this morning. I know the relationship, but I never remember the name. Okay, hopefully. I mean, okay. So what's the relationship? What's the relationship between V and T? What's the relationship? V, T, they're proportional to each other. More precisely. Can I write something like this? V equals to alpha T? Are you sure? Okay. The experiment result looks like this. Okay? The experiment result looks like this. This is T. This one is V. Okay? Let's use the degree Celsius. Okay, it's linear. Okay? And linear. And linear. Okay? It doesn't go to 0. Okay? It doesn't go to 0. Right? Instead, you need to add another parameter, another constant here. Right? You need to add another constant here. So what's the other constant? I mean, experimentally, okay? Experimentally. If you do the extend the line to the other side, you will find it always come to the same point, okay? So what's this point? Yeah, what's the name of it? And what's the number? Temperature of 0, absolute 0, absolute 0 in degrees Celsius minus 273.15. Okay. Okay. And then we redefine the temperature. Luckily, we do not use Fahrenheit. We use the degree Celsius. Okay. That's make it very well trouble in the United States, but doesn't matter. Okay. Since that in mathematical calculation, we do not use Fahrenheit. We use either degree Celsius or Kelvin. Okay. So 1 Kelvin, basically, the Kelvin equals to degree Celsius. What? Huh? Plus. Okay. This is a very simple relationship. Basically, this is the T naught here. Okay. So if we redefine the temperature, then is what? V divided by T equals to a constant, right? Correct? But this is only applied to the thermodynamic temperature or Kelvin, or absolute temperature. Okay? You know what I'm saying? Doesn't apply to degree. Does not. If you want to use the degree centigrade or like Fahrenheit, this equation doesn't work anymore. Okay? This only works for the absolute temperature.
The K that you have written there, is that the same K that you had written earlier when defining temperature?
No. That's written. This K is a unit. It's Kelvin. Okay? It's Kelvin. And for that K, on purpose, I write it in that way. Okay? This is the Boltzmann constant. Okay, what's the number of it? 1.38 10 to the negative what? 23 unit. What's the unit? Joule per Kelvin. All right? Just erase it as quick as I can, just in case you're wrong. Do not leave any evidence. I made a mistake. You know that when I was talking in the physics department, I thought, oh, this one equals 1.3 10 to the order of 32. No, it's not 32. It's the 23. Oh, really? Forget about it. Keep.
And is that C like degrees Celsius?
Huh?
That C is for
That C is the degree Celsius. Be very careful about the unit, though. Be very careful about the unit. So especially United States, okay, because we mix the unit of quite often. How many of you do experiment, not theoretical work? How many of you do in the lab, work in the lab? Everybody work in the lab? 1 inch equals to how many millimeter?
25.4.
Huh?
25.4.
1 inch equals to 25.4. Is that exact?
That's what I had in my brain.
Huh? Do you think it's exact or not?
No. Approximate.
It's exact, okay? That's exact. Because after we define millimeter, people redefine the inch. Okay? That is exact, okay? And but you still may have some trouble, okay? Let me tell you the history of the one very stupid and interesting famous mistake NASA made. Have you heard about it? NASA sent a rover to the Mars. And then the machine, the rover was designed by NASA. And the thrust, the engine was fabricated by Lockheed Martin. Everybody knows Lockheed Martin, right? He support the entire, they support we have a lot of money from them. They have the computer flights. And then, when I want to land on probably Earth or probably Mars or Moon, I forgot. When you want to land, they send the data, they have to communicate, okay? The rover itself have computers calculate how much thrust you need to put on the engine. And engine receive the signal, give some air or whatever to slow it down, deaccelerate, make it land on Mars safely. But eventually, it's collapse onto the surface. Do you know what's the reason for that? They use different unit. NASA uses the pressure NASA uses is the Pascal or Newton per meter squared. And the Lockheed Martin use the imperial unit. Okay, that's the pound per inch square. Okay? They only give a number, but they do not unify the unit. Okay? Yeah, you can see that that's the disaster happened. Okay. So try our best. When you do this kind of scientific stuff, when you do the calculation, try to avoid use multiple, unit. Okay, you can either use imperial or you use the metric. Okay, but do not mix them. Okay? So for thermodynamics, my suggestion is either use the degree Celsius or use the Kelvin. Okay, we don't use the Fahrenheit. Okay, and I don't use the PSI. Okay, we use the Pascal. Okay? Another question. Another very mysterious unit. Ounce. Have you ever heard about it?
Yes. Which one?
He got the point. Which one? What about the liquid ounce? 1 ounce equals to how many millimeter? Milliliter. You don't know? How many different ounces you know?
Because I know there's like the ounces of gold, right? The
Yeah,
troy
liquid ounce, yeah.
Fluid ounce.
Yeah.
And like me, I just think like an ounce, there's 16 of them in a pound. I don't know which one that's called.
Yeah. That is probably just like the basically two types of ounce, right?
At
One
least.
is
At least.
Yeah, one is weight. The other is volume, right? Okay, that's the reason I'm a professor. I know 3 different types of ounce, and one is liquid. The other 2 are weights. Okay, so if you see that the 1 ounce of water, that's the liquid. Okay, I'm saying that 1 ounce of meat and 1 ounce of gold, you know that the weights are different. Yeah. And if you talk about 1 ounce of meat, what's the 1 ounce of meat? What is equals to, or 1 ounce? Equals to how many
28
grams?
grams.
Huh?
28 grams.
28 grams? About, right? What about 1 ounce of gold? Is equal to 32 something grams. Okay? This one is called the troy ounce. Okay? Interesting, right? What about the 1 ounce of 1 ounce of water? How many milliliter? Probably 32 millimeter, right? Or 28 millimeter. They are roughly the same because 1 millimeter of the water is 1 gram, right? So it's similar to one of this, but I forgot which one. But for weight, you have to be very specific what kind of object you're talking about. If you're talking about the metals, especially this kind of gold, silver, platinum, it goes to here. It's called troy ounce. Okay, if you talk about the meat or rice or whatever, ions. Okay, this is the other one. Okay. Very confusing, right? But if you go to like the precious metal exchange, you will not make mistake. Okay, you'll lose the full gram. Nobody wants to happen. But anyway, let's go back to the class. So we combine these 2 laws. We can combine these 2 laws, right? What do we have? We have the PV divided by T. This one will become a constant. Correct? This is the ideal case. This is the ideal gas, right? Okay, so then we have another definition. We have constant here, and we talk about if we have one more of the gas, then the constant is defined by R. Okay, R becomes the ideal gas constant, right? This is equals to what? 8.1, right? right? And what's the unit?
Grounds.
What's the unit?
Is it grounds?
I forgot. Okay, you're gonna check it. What's the unit? Okay, this homework. What is the unit? But you should be able to check. Okay, you should be able to check. Let me tell you how you can check it.
Joules per Kelvin.
Yeah, roughly. What about this one? P times V. What's the unit of P times V?
Joules.
It's joule, right? It's joule, right? Correct? Because P is pressure, V is volume. So P times volume is volt, right? So how much work we do is in the unit of joule, right? It's J. T is Kelvin, right? But do you think the R is a unit of joule per Kelvin?
Per mole.
Per mole, right? This is unit. All right. So, and then this one equals to 1 at 8.31 joule per Kelvin per mole. But if you have the more gas, then you just times N, right? N is the amount of the matter, correct? So then this is the ideal gas equation, right? More properly, I mean, most of the case people write it that way. PV equals nRT, this is the ideal case, correct, everybody? And we use this equation to start our topic through the semester, okay? All right, so the, how many time we have? We build out the foundation, okay? Make sure that we can resonate, we have the same language. All right, so start from there. The next task we're going to do is to briefly introduce the thermodynamic laws, okay? We have the thermodynamic first law, second law, third law, okay? We have different laws, okay? So, how these laws happen, why this come from, and what's the reason for them? Let me do not talk about laws, okay? Let me review the history, okay? I think that's easier way for us to do the job. So you know that when people start to feel interested about thermodynamics, when that start? Why people want to start study the thermodynamics? What's the trigger point? No one knows history of it?
Like Boltzmann?
Huh?
You know, like Boltzmann?
No, that's afterward.
Okay.
So what's the unit of the power? What's his work?
Kilojoules per second.
Yeah, joule, we have watts. That's all human being names, right? So what's the most famous thing? What's the most famous job Watts did?
Invention of steam engine.
That's a misleading concept, okay? So what is the job of the Edison? What's the most famous invention of Edison?
Light bulb.
Light bulb. So this is not correct, okay? The most proper statement is that Watts improved the engine efficiency, and Edison increased the lifetime of the bulb, okay? He did not invent it, okay? But anyway, so Watts, okay? So this guy, okay? That's the reason we put the power in his name, okay? Just to memorize it. But what's the reason why we want to increase the efficiency of the steam engine? What's the reason for that? This is just during the first industrial revolution happened in British, right? So people use this steam engine to drive the machine to produce in the industry, right? And at that time, people do not know what is heat, do not know what is work, okay? And then they find that if you warm up the water can do the work, can drive the machine, okay? And then people start to understand, okay, there's some energy inside. There's some energy inside, okay? People at that time do not have the concept of energy, okay? They only know that they can start to do the work. And then they start to think about, is there any way we can invent kind of machine can run forever? What's the name of the machine? Huh? Louder? What's the name of the machine? Can run forever?
Perpetual motion.
Yeah. I have difficulty to pronounce. It's called a potential machine.
Yeah, perpetual motion.
Yeah, something like that. That means without input any energy, but it can drive, can output power continuously forever, right? And people spend quite a lot of time to invent this machine. I have here some slides, but I did not put it there. It's something like this, right? It's something like this. Okay, you can find it online. So I don't put on slides because there's not quite much information, but you can check online. It's like the potential machine. You can find it everywhere. So basically, you have to spend a lot of time, spend a lot of years, different kind of patterns in the search online still exist, but nobody successful. Even if you check on YouTube, you still can find this kind of interest. And people kind of wires and light bulbs start rotating, and they generate the light or whatever. All of them fake, okay?
Or it's
But-
reversed.
Huh?
Or they put it in reverse.
Yeah. But sometimes I also think, what's the principle of it? Myself also have, okay, is it really possible? I think if I question that inside the class, or even talk about it in the class, probably my university going to revoke my degree. But anyway, so eventually people realize, okay, then who changed the entire past? Who stopped this kind of stupid case for the perpetual machine? What's the name of the person?
Something you just said?
Okay, so people just looking for have different kind of solution to build this kind of perpetual machine, right? Who was the guy saying that, okay, this is totally wrong. This is dead end. And prove this is dead end experimentally.
What?
You know what? It's Joule, okay? What is the experiment? He demonstrated that the heat can be changed into the energy, can be changed into the work, or the work can be changed into the heat. But the total amount never change, right? He did some experiment that you can use the water, and then you can put some mechanical structure inside it, and probably some turbine inside, and drive the turbine with some weight. Okay, to find that because at that moment, people already know the energy from Newton, right? They know that the potential energy always changes with the heat. Okay, but the heat can also change with momentum energy, but they always keep the same, okay? That means the dq is always equal to dw, okay? W is work. Okay? That means we cannot create the work or energy out of nothing. The work, that means energy is conserved. It can only change from one form to the other form, okay? And right now, we know we have read the equation in that way. The du, or dE, okay? du is the internal energy equals to what? dq, and then plus, it depends on how to define the direction of the work, okay? Probably can define it that way, okay? Then the positive sign means the system doing some work to the outside, okay? That means that's the reason we have negative sign here, okay? If they're doing work to the outside, then the total internal energy got decreased, right? If the external doing some work to the object, then the total energy got increase. That's the reason it depends on how you define the direction of the work, okay? You know something? But you can also put negative sign or positive sign, but you need to tell people the definition first, okay? And then we know that the work can only change from the, if the total energy doesn't change, the work can be changed to the heat, or heat can be changed into the work, right? But we cannot create the energy out of nothing. Okay? So this is the first law of thermodynamics. Okay, what's the problem to solve? It only tells us we cannot build the perpetual machine. That's it. Because of what? Because of the conservation of energy. Right? We cannot get energy out of nothing. But more precisely, as I mentioned, W is kind of like the, we know the definition. If we apply to the ideal gas, it's dV. Right? P is the thermodynamic parameter, V is thermodynamic parameter. But the work is not, okay? Work is not, okay? P is ease. Q is not, right? Q is not a thermodynamic parameter, right? We cannot write it in the term of exact differential, right? So sometimes, in order to distinguish the exact differential and non-exact differential, we can add something. And sometimes, some textbooks, we add a small bar here, just to indicate this is not a thermodynamic parameter, or this is not exact differential. We just add a small bar here, but it's not always necessary. If you know this one is not a thermodynamic process.
What is Q?
Q is the heat. Yes, Q is heat. and the W is work, and U is the internal energy. Okay, we use the U for internal energy because E is sometimes used for something else, especially if we want to apply the thermodynamics to some electromagnetic systems. We use E to label the electric field, right? So we cannot use E for the internal energy anymore. So we use the U instead, okay, for most of the cases. Again, let me write it down for you to. This one is the internal energy. Okay, the Q is the heat, and W is the work. Again, W is another example. This W is not a thermodynamic parameter. Okay? It depends on the process, correct? It depends on the process. Okay? And you know that PV, without pressure, volume, you already know that one. Okay? So basically, this is the first thermal. This is the first thermodynamics law. Okay, so, and the afterward, we come to another question. Okay, the first law tells us that the energy cannot be created, is only changed from one form to the other one, correct? Then people have another idea. So since that we have the engine, right? We have the engine. So is that possible? For example, I think my cup is colder than his cup, right? There's no liquid, condensed outside. The question is, if we have 2 cups of water, so is that possible for the energy of the one cup transferred to the other one to make the cold water even colder and warm water even warmer? Think about it. So we have this cup of water. We know that these have internal energy inside. Right? We know that these have the internal energy inside because these have temperature, right? Can we make use of this kind of thermal energy to drive the engine? We know that no, but what's the reason?
It's colder in the room.
Huh?
It's just gonna
It's
keep
colder
running.
in Rome, right? This is a very statement is very intuitive, correct? Because it's colder in the room, we cannot take energy out of it anymore, correct? And there's something. But why this happened? Why this one? If this one is colder in the room, then the atmosphere it cannot release energy anymore. Why not? Huh?
Because of entropy?
Yeah, that's the afterword. That's the afterword. That's a problem of most of the thermodynamic textbooks. They reverse, they talk about theory first, they do not review the history. And that's really got confused why we have the definition. Okay? The entropy basically is a byproduct. Entropy is kind of byproduct. People want to study why this happened first, and then people find that this is another parameter related to the process. We call it entropy. Okay? We even don't know why you call it entropy. What's the name? What's the meaning of entropy? Where it's from? I don't know. What's the name? Why it's called entropy? Anyway, so we know that it's impossible, right? But why is it impossible? For that one, I think even there's nobody bothered to do the experiment. Not like the perpetual machine. People still try to build up different type of, but even nobody bothered to get energy out of this kind of cold cup of water, right? People know that it's impossible, right? But why is it impossible, right? Because the thermodynamics, first of all, did not tell us it's impossible. It only tells us, okay, this cup of water have a lot of internal energy, but we cannot make use of them. What's the reason for that, right? And then, from that one, we start to talk about the second. People do not know. People actually do not know. Until there's another person still want to increase the efficiency of the engine. And then from that theory, people start to understand why we cannot get energy from the single heat source, or why we cannot take the energy out of this cold water. Okay? Basically, this is the second law of thermodynamics. So what is the second law of thermodynamics? Basically, I think in order to understand that one, we need to talk about this stuff. Have you heard about the, what's this, let me just put it. Let me put this equation here. du equals to dq minus dw. Okay, this is the first one. Okay. The second one. There's the time stop, not done. We're going to introduce something about this one, okay? How to pronounce this? Carnot. I think, oh.
Did you want to?
Yeah. And my question is that how I make sure that the camera can see me.
Sure, let me see what we see on the picture.
Anyway, that's the beauty. How to pronounce it? Carnot. What's the original of this thing?
Person, right?
Huh?
You said the
What's the
person
original
name.
name? What's the language of this? Is that English?
English.
French.
French.
French?
Yeah, Cardinal.
Carnot. I think it's Carnot. It's not something. Oh, by the way, so yeah. How does it see that one? Ampere. What's the unit of it?
Amps.
Amps is the current, right? But you know that this is French name, right?
Yeah, you bastardize it when you say it in English.
Yeah. Ampere or whatever. And actually the original spelling looks like this, right? It has small prime on it. So how to pronounce that one? I asked the French guy about how to pronounce. The pronunciation is very interesting. It's called something like the ampere. You have this sound, right? Ampere. I mean, they told me that if I see that one, this comes sound. Anyway, it doesn't matter. But this is definitely not the English word. But anyway, so we call it Carnot or whatever. You know that my pronunciation is not right. Okay. So this guy wants to answer one question. What's the limit of the engine efficiency? What's the limit of the engine efficiency? Let me tell you the conclusion first, okay? And then we can continue to derive the equation next week. Next week. So what he's find is he built up the theoretical model. Okay, we call it the Carnot cycle. Basically, in that kind of cycle, we have two processes. Okay, one is called the isothermal, that means temperature doesn't change. The other is adiabatic process, that means there's no heat exchange. Okay? The key conclusion he has is you always need to have two thermal sources. We always need to have two thermal sources in order to make the engine work. Okay? You have to take the heat from one heat source, doing the work, and release some heat to the low temperature heat source. Okay? You cannot do the work with only a single heat source. You know what I'm saying? In other words, we cannot take the energy from it. We need to have something colder than it in order to do the job. You know what I'm saying? So this is the key conclusion achieved by this person. Okay? But of course, we have more details. So you can see, the most important thing is the work equals to, for example, you have the heat, you absorb the heat from on this line, and you release some heat on this too. Okay? And the work done by this kind of cycle is the Q1 minus Q2. Correct? And as I mentioned, the Q is not the thermodynamic process, it's not the thermodynamic parameter, and we can make some derivative. But anyway, so the most important thing is about this one. The work is equal to the heat absorbed and the heat released. And then the Q1 divided by Q2 is also equals to T1 divided by T2. Okay? And then the engine efficiency maximum equals to 1 minus T. Okay? That's the maximum engine efficiency you can get. Okay? But of course, from this relationship, we can define the entropy. But I will leave this topic for the next time. Okay? But let's go back to the second law. It tells us the dq is smaller or equals to TdS. We define the entropy. Okay? You know what I'm saying? And when dq equals to TdS, this is a reversible process. When it's less than that, it's non-reversible process. Okay? But anyway, so we're going to continue talking next time. I'm going to talk very quickly, finish the second law of thermodynamics, at the beginning of time, next time, and then we move on, we will go back to the first law to introduce it in details. Okay? Let me know if you have any questions. So, any suggestions? We can improve the class. How could I see whether the camera can see me or not?
That's what I'm trying to figure out. I mean,
Yeah.
it should have worked, but it's not working like that.
Yeah, because the students tell me that they want to make sure that they can see me online. So I need to make sure that I have the right angle.
It should be in the camera thing. I'm gonna reset the, it says there's no signal here, 'cause I think this monitor is meant to show that. But it's not working either, so I need to,
Oh, I see.
it says Flint, so I'm gonna reset to Flint and see if that gets it working.
Should I be here or I can leave?
Oh, you can go if you need to. I just wanted to see if I can. Yeah, if you need.
No, it's fine. If I keep it, I forgot to do it next time.
If you need help next time, you just let us know at the beginning of your class, and we'll come here and try to make sure it's set up for you.
Of course. I mean, I have class next Tuesday, this time as well. All right, thank you. So you guys want to leave? Or you have another class?
Yeah.
Yeah, we have to do this right here then.
Everybody makes fun of me, right? Because I'm not.
Do you guys have difficulty understand what I'm talking about?
No.
It's fine. Yeah. Okay. So you know that my first supervisor, when I first came to the United States, my supervisor told me that, hey, I cannot understand what you're talking about. I can't. You need to. He even showed me a book concept, how to speak English in university. And there's a small chapter, especially for Chinese students. And he also have difficulty to understand the native speakers. There's an Englishman that will give me that. How you have very strong accent, I cannot understand. And then 1 year later, he told us, you know, I went to doctor, he told me that one of my area have issue nearly that. Yeah, okay, that's really you know my problem, it's yours. Private professor. All right, see. Oh, where's my
Your
super?
scooters. If you believe, you can give it to me.
$1,000.
I just did,
Yeah, that one.
yeah.
Okay, see you later.
Right now, my passport. The case, I don't have background.
All right. Are you sure? Thank you so much. I think I need to tell you about it to see whether I have some memory issues.
Yes.
Sure?
Yeah, I think I have said to you.
Oh, you did, okay, I got it.
So, yeah, I didn't tell you. Yeah, that's why I guessed it. Yes.
Restart the system.
Yeah, it is. There are many Indians.
Actually, the first time when you said that you were from, because the first time when I saw you, I thought you were from.
Everyone thinks that,
Yeah.
like,
Then you said that you were from like.
the islands,
Yeah.
so they, what they did.
I know too, the
they-
people
they-
were-
Yeah.
I know it very
They gave us
well.
the curriculum and stuff, and Sharpan actually came last time, not Sharpan.
Oh, Carol, I came through the little hole.
Yeah, yeah,
Okay, so when did you go?
probably like 28 something like that.
Okay,
Yeah.
it was like concert or something.
No, big cricket match.
Oh,
Yeah. You play cricket?
Oh, okay, that league, right? Yeah, it was.
Yeah, yeah, you know, okay.
Yeah, obviously people watch cricket, so.
Oh, okay.
Because there is a league, right? T20s or league or something?
Yeah. Well, I'll see.
Okay, see you later.
okay, bye-bye.
Have a good day.
This is the third semester or second semester?
My third, I have one more next time and I'm
Yes.
done.
Yeah. Congratulations.
Yeah.
Okay, that works.